Hello everyone, welcome to lesson 31 for BC Calculus. In this lesson we're going to discuss volumes by shells and arc length. So volumes by shells is going to be another way you guys can find volume of revolution if for some reason the washer-disk method does not work out. And it actually can become a simpler way of doing it than actually trying to find the washer-disk method. First of all, let's talk about why we would use shells in lieu of washer-disk. So this very small picture that you guys see right here, which I apologize for. So if you see this, and I ask you guys to take this shaded region, so we'll go ahead and shade this right here, and I want to revolve this around the x-axis, sorry, the y-axis. Well, if you guys look at this picture, for example, if I ask you guys to do that, well, remember we did rectangles, right? And rectangles would be perpendicular to our axis of rotation. So if I drew a rectangle right here, then my right curve would be this function right here, this just line, this x equals function, and my left curve would be this line right here. However, if I moved my rectangle up to here, then my right curve would actually be this line that's slanted, and then this would be, again, my left curve. So if we are asked to do this, I would have to do two integrals if I want to do the washer-disk method. So shells actually gives us a way of actually eliminating that and actually be able to do just one integral. So let's talk about how it works, because it actually, like I said, it can be an easier way of doing it. So first of all, what is a shell? So a shell is actually going to be what I consider to be a hollow cylinder. All right, so we're going to basically rotate this, and yeah, it looks a little bit like a washer, but what we're going to end up doing about this guy is that we're going to take this thing and we're going to slice it. We're going to take this cylinder and we're going to slice it. And again, it's hollow because it's inside. And then we're going to unfold it and it's going to become this rectangular prism. And so remember again, and we've said this many times before, that volume, when we integrate that, it's just really going to be the area of whatever we are, the revolution that we're trying to do. So if we're trying to create the volume of the shell, well, again, when we unfold it, it becomes a rectangular prism. So if we can find the area of this rectangular prism and we integrate it, we're going to get the volume of the actual shape. So just back to good old geometry for a minute, our distance, our length here is going to be 2 pi r, right? Because that's the circumference of the circle. Well, that is a circumference of the circle. If we cut it and slice it, then this is going to be a distance of the circle. Well, the width is going to be delta r, or delta x, whatever you want to call it, and the height is going to end up being the function. Or what we've learned before, and what we've been using before, the height is end up going to probably be our f of x function minus our g of x function, right? And if we're looking in terms of x, it's going to be our top function minus our bottom function, and if we're looking at terms of y, it's going to be our right function minus our left function. So let's go ahead and do a couple of examples and see how this works out. Okay, so let's look at example number 1. It says the region bounded by the function y equals 1 over the square root of x, which is right here. The x-axis, clearly right here, x equals 1 is going to be this line right here, and then x equals 4 is right here. And we want to revolve this thing around the y-axis. So this is the exact picture that I was talking about at the very top of the page. The first thing that, again, we always did when we're talking about volume is I go ahead and say, okay, we're going to revolve around the y-axis. So if we did the washer-disk method, remember that we would have to draw a rectangle that was perpendicular to our axis. And so if I drew the rectangle here, well, my right curve would be the function x equals 4, and my left curve would be my function x equals 1. But if I moved my rectangle here, then my right curve would be the function 1 over the square root of x, and the left would be x equals 1. Every example that we did in the last lesson, no matter where we put our rectangle, our top curve and our bottom curve were always the same, or our right curve and our left curve was always the same. Well, in this particular example, we don't do that. So taking all this into account, we're probably thinking, okay, this is probably going to be the shell method. So let's actually talk about the shell method. So the first thing I want you guys to notice is that, again, for washer-disk, our rectangle was always perpendicular to our axis of rotation. Well, in the shell method, our rectangle is going to be parallel to our axis of rotation. And so that's why this box right here was highlighted. Again, I'm just showing it with my little box, but that's what the idea is. So no matter where I draw my rectangle parallel to this axis, it's my top curve is always going to be this, my bottom curve is going to be this. Notice that I'm talking about my top curve, my bottom curve, but again, we're rotating around a vertical line. Well, for the shell method, you're going to always do your function, you're going to always do your integration based on, again, what axis is perpendicular to our rectangle. So it's perpendicular to the x-axis, so this is going to be our change in x. So that's one thing that we have to remember about the shell method versus washer and disk method. But the easy way, guys, to remember this is that whatever, when you draw in your rectangle, whatever is perpendicular, if it's in the x direction or the y direction. So if I'm going to be vertical, then I'm going to be delta x. If I'm going to be horizontal, if my rectangle is horizontal, it's going to be delta y. So let's go ahead and actually now talk about the shell method and how to. So back up here is what I want to use, because I like this better, because it's all about area. So the 2 pi r times the h times the delta r. So let me go ahead and just show you what the shell method is. So we can always pull out, now again, because the shell method, we're going to always pull out a 2 pi. For all the other volumes, we've always pulled out a pi. So 2 pi. The interval of integration is always going to be the same old stuff. Because again, we're in delta x, then our left bound is 1, and our right bound is 4. Now, the radius, and this is how I always do this, and I think this is very helpful. The radius is always going to be from our either y-axis or x-axis, but whatever's parallel to this. So our radius is going to be from the y-axis to our actual rectangle. And the reason why I choose the y-axis is because, again, it's going to be what's parallel to this. I could be rotating around y equals 1, y equals -1, but I'm always going to, my radius is always going to be from one of the axes. So I'm going to say that the radius is always going to be a distance from one of the axes to your rectangle. And so from here to here, so this is going to be x. So let's go ahead and call this our x. Now, we're going to show you an example a little bit later on that the radius is not just simply x or y, because I don't want you guys to think it's going to always be x or y, but in this case it is. And then we're going to look at our height. Where our height, guys, is going to be exactly what you've seen before. It's going to be the change in our y, our top function over our bottom function. And again, because the rectangle is vertical, then top minus bottom. So our top function is going to be 1 minus the square root of x. Our bottom function is going to be 0. So minus 0, we are not squaring this. It's just the height, right? There's no squaring in this problem, so there's no squaring in the shell method. And then our delta x is going to be our actual problem. Well, our width, right? It's going to be the width. How wide, how thick is this shell going to be? And so that is it. And then you use your calculator for this problem, and you get 29.3215. So let's go ahead and do one in terms of y, and then in the next video I'm going to show you guys a couple of examples of the shell method where x is not going to be, or the radius is not going to be x or y, but in this one it's going to be. Because again, we want to try to keep it as simple as possible for what we're doing. So for the next one, it says find the volume of the solid revolution revolved around the region bound by the graph of x equals e to the negative y squared, the y-axis and the x-axis. So x-axis, y-axis, and then this is our curve right here. So what we're going to end up doing with this is, again, ladies and gentlemen, if I went and we're revolving around the x-axis, right, as you guys can see right here, revolving around the x-axis. So if I chose a rectangle here, my top curve would be what's cut off, and then bottom curve here. If I did it here, then again, different curve, same curve down here. So this, again, it lets us know that we probably need to use the shell method. So, as you guys can see, and I'm not going to taint this little color right here. I'm going to just leave it alone, but this is going to be our rectangle, and you guys can see that it's now parallel to my axis of rotation. Since it is parallel to this axis of rotation, it is perpendicular to the y-axis, and so again, whatever the rectangle is perpendicular to is going to be in terms of y. So, that's what we're going to do. Well, let's go ahead and find the volume of our function, and we're going to use the shell method. So we're going to do 2 pi. And so it tells us here that we're going to go from 0 to 1. All right, because we didn't really know what to do with this, and we had to been told either this or it was bounded by the line y equals 1. So if they didn't give us this, they would say, okay, we also need to bound by the line y equals 1, and that's how they would draw this line for us to bound it. So this is already given to us. So again, the radius is going to be from your rectangle to the axis that's parallel to it. So that's why you guys can see that they're telling us that the radius is going to be y. So y equals the radius. Well, in our area, right, it's just going to be 2 pi r times height times delta y. So that's going to be our y. Well, our height is going to be our right bound function minus our left bound function. And it's very convenient for us that they've already given this to us in terms of y. So our right function is going to be e to the negative y squared. And then our left function is going to be minus 0. And again, you don't have to put the minus 0 in there if you don't need to. And after that, we just have to now do our width, the width of our rectangle, which is going to be our delta y. And I know I did that one much, much faster, so hopefully that made sense to you guys. And the calculator, it gives you 1.9859. So let us go through one more question. To save some time, I went ahead and draw a really horrible picture for this. Let's show you guys where our radius is actually not going to simply be x or y, because that's, I think, the more important thing to do with these problems. So example 3 says, find the volume of the solid of revolution formed by the region graphed by y equals x cubed, which is right here, x equals 1, and then the x-axis. And we want to revolve this around the line y equals 1. So we want to revolve this around the line y equals 1. And so I know right now, this is y equals 1, and we're revolving this, that if I plugged in 1 here for y, x would also be 1. So it actually is very convenient for us, and it's nice for us that this all intersects at this one point. Now I just want to say really quickly, we can actually do this problem in both washer-disk method, and we can do it with the shell method. So I'm going to show you both. I'm going to show you both ways. So what I talked to you guys about in lesson 30 is that we could essentially draw our rectangle perpendicular, right? So this is the washer-disk method. So I'll do this as the W and A method. And then I'll show you guys the shell method. So just so you guys get a feel for what to do for each one of these. And this also is a good refresher on what to do for the washer-disk method and how different they were. So if we're perpendicular, my top function and my bottom function are always going to be the same. Now, because my axis rotation has a gap, right? It's not completely, my region is not flush with my axis rotation. This is going to be a washer. And so we're going to have to do, a big R and a little r. But let's go ahead and show you how to do this problem. So volume is going to be equal to pi. Remember, for washer disk, we only pull out a pi. And we're going to integrate from 0 to 1. Oh, and by the way, because our axis of rotation is perpendicular to the x-axis, everything's all about the x. Right, so we're all about the x here. And again, does it matter which one you choose? No, you do which one is easiest for you. So there's no right or wrong answer unless the question specifies you have to use a particular method. So anyway, 0 to 1. And then our big R is going to be, again, the axis of rotation is above the curve. So it's going to be the axis of rotation minus our curve that is the furthest away, which is going to be x equals 0. So our big R is going to be 1. And again, ladies and gentlemen, you guys know that distance is 1. Our little r is going to be the axis of rotation. And again, because it's above the x-axis, it's always top minus bottom. And we're going to subtract from that our little, the function that's the closest, right? Our little r is this little guy right here, right? That's our little r right there. So it's going to be 1 minus x cubed. And so for this problem, we're going to do 1, and we have to square big R. We're going to subtract little r squared dx. And then that's how we would get that actual answer. Now, if we want to use the shell method, then we're going to do volume. Now remember, shell method, we want our rectangle to be parallel to our axis of rotation. And so we're going to go ahead and do that. And again, our right-hand curve and our left-hand curve are all the same, so this works out. Now, if we're doing it this way, remember, we're perpendicular to the y-axis, right? We're perpendicular to the y-axis. So that means this is going to be a change in y. So the only thing we have to do really quickly to fix this problem is we need to solve for this. And so we got to find out what x is equal to. Well, x is going to be equal to this cube root of y. And that's pretty easy to do. Just rewrite that as x equals the cube root of y. So we want this now to be, this function to be that, right? X is equal to the cube root of y. So we're going to go ahead and pull out the 2 pi. We're going to now integrate with our change in y. Now this example, it's actually nice that it ends up still being 0 to 1, but remember we still want our lower bound and our top bound. So this 0 and 1 is actually different from this 0 1. This top one is from here to here, and this one's from here to here. So you want to be very careful about your bounds. And so now The y, the radius, is actually going to be right here. It's always from your axis to your rectangle. So this is going to be y. So the radius, and I'm getting a lot of color here and I do apologize, but the radius is going to be how far from the axis of rotation it is to our rectangle. So this is our radius. So again, the y, I always tell you guys to do y and x from your axis of rotation to your rectangle. So the radius is going to be, well, this whole distance here is 1. So our radius is going to be equal to 1 minus y. Let's look at that and make sure this makes sense. So if this whole thing right here is 1, and I want to subtract this tiny distance, which is y, then this, what's left over, is going to actually be 1. So I know you guys probably don't need to see this, but you know, it's me and I want to show you this. So if this distance is y and this is our r, well, our r is going to be, this whole thing is 1. If I take and subtract y from it, I'm going to get r, right? Or think about it like this, y plus r is equal to 1, and if I solve for r, I get 1 minus y. So my new r in this case is going to be 1 minus y. Y minus y. The height is always the same as before. It's going to be our right-hand side minus our left-hand side. So our right-hand side is going to be x equals 1, so it's going to be 1 minus our left-hand side, which you guys can see right here is going to be the cube root of y. And so, and this is our dy. So what we have done here is we have created the radius, this is the height, and this is our change in our y, or our thickness, if you will, or a change in our radius, whatever you want to do. So 2 pi r circumference, height, and then change in y. All right, so hopefully that's helpful for you guys. In the next video, I'm going to show you guys a problem where we're going to do washers, dish, shells all together for you to see the difference. So come back in the next video when we do more practice on the shell method and more review for washer and disc. And by the way, I don't know why I wrote an A right here. I just realized this, so I'm keeping the video going one more time. That should be D. What was I thinking? So, sorry.